Okay, class 12. The topic that we are going to start today is electric current. All right. Okay. So from today onwards, remember, see, so far what we were discussing is electrostatics. Okay. We spoke about Coulomb's law, Gauss's theorem, and potential, electric field, capacitors. All right. In all of those topics, remember, actually, we considered our charge, okay, that is an electron, a free electron, to be what is it called, to be stationary. All right, the charge was not moving, the electron was not moving. All right, so from today onwards, what happens is, as you already know, electric current is defined as the rate of flow of charge. All right, so electron has started moving, the electron is mobile. All right, so if delta q be the charge flowing in time delta t, so delta q is the charge that is flowing in time delta t, therefore electric current is delta q by delta t, rate of flow of charge. Now if time is very small, delta t tends to 0, in the limit that delta t tends to 0, electric current is also written this way, dq by dt. All right, so it basically is charge divided by time. All right, so don't forget this definition of electric current. Okay, so with this I don't want my video to be very long. Okay, so let me jump to the topic. Today what we are going to discuss about is the theory of how electric current comes into play. All right, so mechanism of flow of current. All right, now say for example this is a conductor. Now inside this conductor we know that there are plenty of free electrons. There are a number of free electrons. Okay, now this is an isolated conductor. We have not isolated in the sense that we haven't connected it to any external power source. So therefore the electrons, these are free electrons, mind you. Okay, we'll only be talking about free electrons. So these free electrons will be randomly moving in all possible directions. Okay, inside any conductor, inside any isolated conductor, we have free electrons moving randomly in all possible directions. Okay, this is a very random motion. All right, now how is this possible? This is possible because of the thermal energy that the conductor possesses. All right, okay, so therefore these are also called thermal velocities. So u1, small u1, u2, u3, u4, u5, u, and there are a number of free electrons, and it goes on. Okay, so all of these electrons, they possess certain thermal velocities. Okay, and in the process of them moving randomly, what happens is very often they collide with each other, or they may also collide with I haven't depicted that in the picture yet. There are ions. Okay, we have ions here. From these were actually atoms. From these atoms, free electrons jumped out. All right, valence electron jumped out and became free electrons. So therefore it becomes an ion now. So the electrons, in the process of moving randomly, it collides with each other. All right, it also collides with these kind of ions. You have plenty of ions too. All right, and they are moving randomly in all possible directions. But whatever the case, the average or the net thermal velocity of the electrons inside this conductor, which I'm denoting by U net or U average, okay, which is of course equal to u1, u2 plus u2 plus dot 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 plus un, divided by capital N, where capital N, mind you, is the total number of electrons, free electrons inside this conductor. The u net or u average will be 0. The thermal velocity will be 0, remember. Okay, don't forget this. The net or the average thermal velocity will be 0. Okay, next, now the same conductor, all right, what we now do is we connect this conductor to an external power source, which is a battery. All right, whose positive terminal of course is here and the negative terminal is here. So what happens is when we connect this conductor to a battery, what happens is an electric field is set up. Okay, the electric field is E, of course, is directed from the positive terminal to the negative terminal. All right, from the positive charge to the negative charge. So therefore the electric field is generated along this direction. Now since this is the positive side, what happens is I have only showed the picture of one electron over here. Now what happens is this electron, which is of course negatively charged, it is repelled by this negative terminal of the battery, and it is attracted by the positive terminal of the battery. Thereby this electron wants to move in this direction. okay, wants to move in a direction opposite to the electric field. The free electron wants to move in a direction opposite to the electric field. So what happens is, now it wants to come this way, but in the process what happens is it collides with one of the ions, or it could also be an electron it collides with. So it undergoes collision. So because of which what happens is this electron gets drifted in some other direction. It moves in some other direction. Now while moving in that direction also, it might collide with some other, some other ion or some other electron. Okay, say for example, therefore it moves here also it undergoes collision. So it gets drifted in some other direction, again it collides, it moves in some other. So basically what is happening is the movement of, although we have connected an external power source, the movement of the electron basically wants to move towards the positive side, but still the movement of the electron is still random. Okay, it's getting drifted in all possible directions. But here what is happening is effectively this electron effectively is moving in this direction, although it is undergoing numerous collisions. Okay, but still effectively the electron is moving in this direction, that is in a direction opposite to the electric field, that is towards a positive terminal. All right, so remember so what is drift velocity? Now here I have only shown one electron, okay, but the same story is true for other free electrons as well. There are number of millions of free electrons here inside a conductor. The same story is true, the same story as that of this electron is true for the other free electrons also. The other free electrons also undergoes a lot of collisions. Okay, they get drifted in all possible directions, but effectively they move in this direction. All right, so so today we are going to basically talk about a concept which is called drift velocity, depicted by a small v, small d. All right, okay, so drift velocity. So let me first show you the definition of drift velocity here. So what is drift velocity? The average velocity with which electrons move inside a conductor under the influence of an electric field is called drift velocity. So what I have shown here is the electron effectively moving in this direction towards the positive terminal. All right, now it moves with all possible velocities, all right, for one electron. Okay, there are other free electrons. So these free electrons also move with all possible velocities, but they effectively drift towards this side, towards the positive terminal. So therefore the average of all of the velocities of all of the electrons, okay, the average of the velocities with which the electrons move inside the conductor under the influence of an external electric field or potential difference also you can say, okay, is what is called drift velocity, and that is exactly what I've written here. The average velocity with which electrons move inside a conductor under the influence of an electric field is called drift velocity. It's the average velocity. Okay, we are going to look at its expression also. We are going to derive actually its expression also for drift velocity. It's the average velocity, remember. Okay, all right. So straight away I jumped to drift velocity, but let us talk about two other terms also that we'll encounter here. One is called mean free path. Now what is mean free path? The average distance traveled by an electron between two successive collisions is called mean free path, denoted by a lambda. Okay, so two collisions, all right, the average distance traveled. So see, between different collisions the distance the electron travels could be different. All right, could be different, more, less distance traveled here, more distance traveled here. Are you on? Okay, so the I almost said are you understanding? Anyway, of course, are you understanding? All right, so what? So the average distance that the electron travels, okay, between two successive collisions, the average distance the electron travels between two successive collisions is what is called mean free path. Likewise, relaxation time, denoted by a tau, okay, the average time taken between two successive collisions is called tau. All right, relaxation time, as the name suggests, is the average time, okay, taken between two successive collisions. So here shorter time, longer time, okay, longer time, like that. All right, so the average of the time between two successive collisions is what is called relaxation time. Okay, so this is mean free path, relaxation time, and drift velocity. All right, so we move to another page. So here, okay, now due to the electric field E set up, all right, so what is happening here is due to the external potential difference that is applied over here, this is capital V, by the way. Whenever I write or I mention potential difference, remember it is denoted by a capital V, okay, whereas whenever I mention velocity, okay, it is denoted by a small d, a small v. Remember, small v denotes velocity and capital V denotes potential. Okay, so don't get confused, this capital V, this small v. Okay, so due to this external electric field applied, okay, this electric field and this, due to the external potential difference applied, an electric field has been set up here. Now due to this electric field setup, okay, the charges, electrons basically are charges, so these electrons are placed in the electric field. Now, so from electrostatics itself, we already know that whenever we have a charge placed in an electric field, it experiences a force. Okay, so that is exactly what I've written here. Due to the electric field setup, the force experienced by an electron is given by F, which is QE, we know this. But Q here is the electron in this case, so therefore force experienced by the electron is minus E into capital E. Why the minus sign? Because the electron is basically negative in charge, therefore it'll experience a force in this direction, opposite to the electric field. It experiences a force in this direction opposite to the electric field. That is why the minus sign, remember. Okay, so now we know from Newton's law of motion that whenever a force is experienced by something, by a body, okay, it accelerates. Okay, so the acceleration produced, A, is force upon m, where m is the mass of the electron, don't forget. Okay, so acceleration is F by m, which is equal to minus E capital E by small m, minus EE by small m. All right, so that is what I've written here. A is minus EE by small m. Of course, we can do away with this minus sign also, of course, don't forget. Okay, now since we know, I have written another expression for acceleration here. Acceleration is minus EV by ml. Now why this? Because we know electric field is the gradient of potential. Gradient of potential meaning basically potential divided by some distance. Okay, now what I forgot to mention here is if L is the length of the conductor, all right, so the electric field is applied across this length, across this conductor having length L. Okay, so therefore electric field here is the gradient V of potential, which is V upon distance. Okay, so just substituting for E, we have A is minus EV by ml. All right, next, if V1, V2, V3, these are all small v's, so V1, V2, V3, Vn be the velocities, since velocities therefore small v's, velocities that different electrons gain due to the application of the potential difference or the electric field. All right, now here, like I already mentioned, here we have shown the story of one electron, but we told you, I told you, the same is the story for different other electrons too. Okay, so if V is the velocity gained by the first electron, V2 is the velocity gained by the second electron, okay, then I can write V1 is U1 plus A tau 1. Now where do I get this relation from? Equations of motion. This is one of the equations of motion. V is U plus AT. Now what is U1? U1 was the thermal velocity that the first electron possessed. U1 was the thermal velocity that the first electron possessed. So before we applied the external potential difference, the velocity, the initial velocity that the electron had was the thermal velocity itself. Okay, so for the first electron, so V1 is U1, the initial velocity of the first electron, the thermal velocity of it, plus A, its acceleration, into tau 1, where tau 1 is the relaxation time of the first electron, where tau 1 is the average time between two successive collisions for the first electron. Okay, is the relaxation time for the first electron. So tau 1. Okay, we are considering that the relaxation time for any of the electrons is the same. Okay, the relaxation time for the first electron, say for example, it started from here. Okay, so you can see the distance it travels here is shorter. Okay, so therefore the relaxation time should have been shorter here. Okay, all right, but we are, for all of these collisions, we are assuming that the relaxation time is same, which is tau 1. All right, so therefore v1 is u1 plus a tau 1. Likewise, for the second electron, v2 is u2 plus a tau 2. v3 u3 plus a tau 3 dot 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 dot. Likewise, vn, we have un plus a tau n. Okay, so what is drift velocity? Therefore, drift velocity, like we already mentioned in the definition, is the average velocity with which the electron drifts. So therefore vd is the average of v1 plus of v1, v2, v3 and vn, v1 plus v2 plus v3 plus dot 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 dot, dot plus vn divided by capital N, where n, capital N, don't forget, it's still the total number of free electrons. All right, so substituting for v1, v2s, so vd becomes u1 plus a tau 1 plus u2 plus a tau 2 plus dot 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 dot, dot plus un plus a tau n divided by capital N, or vd is equal to separating these terms. So you look at the mathematics, u1 plus u2 plus dot dot un divided by n plus a into tau 1 plus tau 2 dot 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 plus tau n divided by n. Now what do we know is, we've already seen that the average of the thermal velocity is 0. This is what we mentioned at the very beginning. The average of the thermal velocity, or the net velocity, was 0, equal to 0, as you can see here. Okay, so this is 0, so we are only left with this term. All right, so vd is a tau. Now what is a tau? Tau here is tau 1 plus tau 2 plus dot 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 plus tau n divided by capital N. Now this is something called the average relaxation time. Okay, in some books you might also see tau average written over here. Okay, but in your book you'll only see this tau average actually is referred to as relaxation time. Okay, it is not specifically called tau average, it is called relaxation time simply. Okay, that is the average of the time taken by the electrons between two successive collisions. We are saying tau 1 is the average, is the time taken by the first electron between two successive collisions. Tau 2 is the time taken by the second electron between two successive collisions. So therefore average of the time taken between two successive collisions is the relaxation time. In some books you might see this specifically to be mentioned as average relaxation time. So substituting for a, now we already know a is E, capital E by m. I'm doing away with the negative sign here. All right, so okay, let me include the minus sign. So vd is minus E, capital E by m into tau, or vd is minus E, capital V by ml into tau. Okay, so don't forget these expressions for the drift velocity. So these are the expressions for drift velocity. Vd is minus E, capital E by m tau. Again, minus sign tells us that the drift velocity is in the direction opposite to that of the electric field. Okay, that is what the minus sign represents. So this is the expression for drift velocity, remember. I'm going to make another video. All right, till then, thank you.